Hello and welcome back to the Hyperthesis episode 92. Today we have a very special guest, Abhishake. My name is Feely.
Hi, I'm Abhishake.
And I'm Liam.
Well, as you can hear, we have Abhishake Goyal, who are joining us as the guest today from Queen's University. He's working in the Laboratory of Organic Photonics and Iontronics with Professor Kuen Kao. He's a PhD candidate here. Welcome. All right, so I don't know too much about, well, I know a little bit about photonics and Iontronics, and we will hear that from you later. But I heard today, Liam, you got an intro topic for us to start.
Yes. So there's this article I found in a website called SciTech Daily that discusses a paper titled Exact Quantum Electrodynamics of Radiative Photonic Environments that was published in Physical Review Letters in November by some physicists from the University of Birmingham in the United Kingdom. And they claim that this research, for the first time, kind of defines the precise shape of a photon and how it kind of interacts with some atoms in its environment. So that's a really catchy title. So I was like, all right, let's have a read. So, I mean, we've talked about photons before, but photons are kind of both electromagnetic waves and particles of light at the same time. That's the whole kind of like wave-particle duality thing in quantum mechanics. And apparently this research kind of reveals how photons are emitted from kind of molecules or atoms, and how as they kind of traverse through their environment, how their shape is influenced by it. And so the physicists were kind of interested in this interaction, and as a byproduct, they kind of found that you can actually, with this new theory they developed, produce quote-unquote an image of a photon, which is something that apparently we don't have yet in physics, which it's not like a picture, it's like an image of, like, apparently it's like energy levels or something like that, and it kind of looks like a lemon, which is neat.
Yeah, it looks like a weird green lemon, but is it like an interaction surface that they were showing? Because that's from simulation, is it not?
So I have no idea. The way I imagine this, um, all right, so I was going to save this until the end of the intro topic, but part of the reason that I kind of thought, not just because it's like an interesting, the shape of a photon, that's like a fun catchphrase, or sorry, like title, but part of the reason I thought this was interesting was because the article is very normally in like physics and science, you have to communicate hardcore science to the public, and that's not an easy thing to do. So you have to kind of simplify things and maybe leave out details. When I talk about quantum mechanics to kids, I don't start going off about how the Schrodinger equation is a first order in time, second order in position, partial differential equation, right? Like, you don't start with the hard stuff. You start with like the easy concepts and simplify things. But this article was it felt like it was written by AI, kind of, and it like kind of never really said anything. It just said like, "Oh, quantum mechanics, like this is going to revolutionize, under our understanding of light matter interactions," and it kind of just like hand waved its way around and never actually said what was going on. And so I looked at the actual paper itself, and the paper itself doesn't even, this lemon looking photo that they said is like, here's the image of the photon, it's not even in the paper at all. So I don't know where they got it from. I'm sure
Yeah,
I'm sure
I
it's,
noticed that too.
yeah, I mean, maybe I was gonna say I'm sure it's legit, but I don't know, because like if you read the article, it just feels like it's written by AI. um so I thought that was kind of interesting, that like it made me think about how stuff is communicated, and I went and looked up some YouTube videos on this, and all the YouTube videos talking about this that came out in the last, week or 2 weeks or whatever, they did kind of the same thing. They just like they had like fun photos of sci-fi physics things happening while they talked, and then they just talked about how like, oh, here's the shape of a photon, and it's like a light matter interaction. They never actually like say anything, but one guy, um, there's this famous physics thing where they use like really high precision cameras to look at light moving through a water bottle. So it's like a bottle of Coca Cola or something with filled with water, and you can like see the little blob of light moving through it. It's like a camera that's so good that it can slow down the speed of light, and you can actually see it moving through the bottle as you send like a light pulse through it. And this lemon kind of looks like a little cross section of that in some sense. Um, I don't know if that's the case, but that's what it reminded me of.
Well, if you look at the author of the article, it's the University of Birmingham. So
Yeah, there's
it's
no
like,
like normally with these articles, it's like someone's job is to like communicate. They have like science communicators, and they're like journalists, right? So they'll read the paper and like summarize it in a way that makes a bit more sense if you're not an expert in the field. Um, and there's no author here, so I'm like maybe it was AI generated, right?
yeah, I don't know.
Um, so the article, if we um,
I mean,
if
it's
we
just showing the intensity of eigen modes, right?
yeah, so the article talks about how um normally when you normally when you think about light and scientists, you think of like some coherent source of light, and you kind of only care what happens after it's formed and once it's like interacted with something in a very specific way. But apparently, very often you don't really consider what happens to light that dissipates into the environment. You kind of just ignore it and say, well, it's not important for what we care about. Which is like a probably true most of the time. But this article kind of like claims apparently that there's a lot of information that you're losing in this light about what happened during it. Or me, like I don't quite know what information it's talking about, right? Because the article is very vague, and it just says that like there's a lot of information lost in this dispersed light that kind of goes away. But by better understanding light matter interactions, you can really improve apparently um, how we engineer them. We can create better light sensors, improve photovoltaic energy cells, the, and even there's applications in quantum computing, nanophotonic technologies, secure communication, pathogen detection, molecular and chemical controlled reactions. Um, so that's pretty much like that's like mostly just what the article says. It never actually says like how they did this, what happened, what is this lemon image, like where did it come from. I just thought it was very interesting.
Did they mention anything about the medium they have used? Because like light or the photon basically interact different in different medium, right? And when they do the studies in the vacuum systems or ultra high vacuum systems, like in the synchrotron, they try to see the band gap using the photons. But when you see it in the real life, let's say in the Coca-Cola bottle, as you gave, it's very different. So did they mention how do they get the lemon structure? In what medium did they get it? Under what conditions? Thermodynamic
So
condition?
the article didn't say anything on this, but when you go into the paper, apparently it's in like silicon.
Yeah,
And
it's a
the
spherical silicon resonator surrounded by vacuum.
yeah,
But
and
these are
again,
all they're not experimental. These I think these are theoretical findings. So they just solve the equations basically. I think, right? So
yeah. So the
yeah,
article here's the actual abstract of the paper. We present a comprehensive second quantization scheme for radiative photonic devices. We canonically quantize the continuum of photonic eigenmodes by transforming them into a discrete set of pseudomodes that provide a complete and exact description of quantum emitters interacting with electromagnetic environments. This method avoids all reservoir approximations and offers new insights into quantum correlations, accurately capturing all non-Markovian dynamics. This method overcomes challenges in quantizing non-Hermitian systems and is applicable to diverse nanophotonic geometries. So that's definitely not anything in the articles mentioned in there, and like maybe for good reason. It's quite complicated. But the thing that stuck with me is that they avoid all reservoir approximations. So when you do quantum field theory, um, quantum field theory accounts for changing numbers of particles or quasi particles. Usually, at least in like the stuff I do, you have a lot of particles in one big state, and you can kind of consider it like this reservoir bath where you can kind of like get infinite energy out of if you want to. Um, so the fact that they say that this is all, it doesn't do any approximations like that, and it's non-Markovian. So Markovian means that you don't care about your past state, you only care about your current state and how that evolves in time. But this is like it considers like all, or at least some past states as it evolves forward in time. But yeah, the article, yeah, like Feely said, it mentions that the medium silicon, and I think the big thing that these guys are happy about is that they kind of took a problem that you normally can't do any mathematics with, and they made it so that you can solve it now. Because a lot of stuff you can't actually solve in physics, and you have to do like intense simulations. So they probably got some differential equation out of it, and they're like, oh, we can actually solve this numerically or even maybe analytically.
Yeah, I think one of the problem for me is like the title or even the article itself is a little misleading too, right? It is like, well, shaping a photo and make it sounds like we have an experimental way to find it, which is absurd in a sense, like a single photon, right? Like the shape of it. So my guess at the time I was first saw it, it's like, well, probably some kind of like computer or numerical solution or something. And then I see the articles like, well, it's not exactly saying that, right? Like it's strange how that's come from the art, like how the article is written when you go to read the actual paper.
Yeah, if you like, word, you do a control F search in the article and search up keywords, it never once mentions like the shape or anything of the photon. I mean, again, it doesn't even have that lemon picture. So maybe that came directly from the scientists. But my understanding, yeah, it's not like an actual image of a photon, but my understanding is that it's kind of like a picture of the energy landscape, I guess if you want to call it that. The energy eigenmodes, or sorry, eigenvalues or whatever within the silicon resonator. Um, so it's still like pretty interesting stuff, but I thought it was this really interesting example of, in my opinion, like science communication done badly, and maybe I'm missing something, but it just
But the first author did say that like this is an image of a photon that hasn't been seen before in physics. So,
mhm. Yeah. So I didn't get to do as much looking into this as I wanted to. I wanted to do a bit of a deeper dive, on like the people talk about these things. There's like subreddits for physics, and there's forums, and there's a bunch of YouTube videos talking about it. And I only got to look at like a couple of them quickly, um, but they were the ones that seemed the most legit, just from like their title and description and photos. But yeah, I don't know. I just thought it's like a steep slope, right? Because it's very easy convince people, or it's very, I don't know. You see a lot of like science miscommunication a lot, where like some article has like a little side comment and a bullet in like a footnote, and some newspapers like, oh, the world's gonna end because of this. It's like, no, that's not how that works. So people might just think like we've seen a photon before, although we haven't. But we I guess we kind of have in some sense now. It's like the black hole, that famous orange blob, the first picture we took of a black hole. That's like, that's not a black hole at all, right? It's like, it just tells you that one exists because you can't see a black hole by definition.
well,
Um,
but that's actual stitching up of a lot of
yeah,
data, right? But this is
it's
this
light
is not.
that's like circling a black hole.
Yeah, yeah,
Yeah,
yeah.
it's
But
not
like,
like the black hole itself, and like
but
it,
still, those are observations compared to these, which is what a single photon should look like according to theory. Right? So it's not an image of a photon at all, in a sense. Like it's a visualized image of like what it should a single photon should look like when it's trapped or like when it's inside the silicon.
yeah. So anyway, I thought
Well,
that was kind of interesting, but there's more I could talk about, like wave functions. It's like, is the shape of a photon, or maybe not a wave function, but like some kind of field that there's like fields you can use to describe photons, and if you solve that in relativistic quantum mechanics or QFT, would that be the shape of it? But then there's this whole like I don't want to say philosophical, but you start to get into like this kind of wild physics debates. It's like, is a wave function a particle? Like, no, yes and no. So that's something maybe we'll talk about again one day.
Well, thank you, Liam, for the intro topic. And now, so we're gonna get into Abhishake's work and such. I think we have a couple terms that you will be able to clarify for us, which I don't know too much about. All right. So, can you tell us in your lab, basically, you work with photonic devices and organic photonics and iontronics. Could you explain what organic photonics are, and also what the heck is iontronics?
Yeah, so basically, when you do, like let's say you are talking about the photons, you are talking about the electrons. In the same way, if an ion takes part in a process and leads to some phenomena, some electrical phenomena that leads to a generation of, let's say, in easy word, a generation of some light. In my case, that basically may constitute to iontronics. Okay, so now you have ions. So in my device, if I particularly talk about my device, which is LEC, if you have, if you do not have any ions, we will not be able to introduce the doping phenomena. And if we are not able to introduce the doping phenomena, we will not be able to generate the light eventually.
So, ions, in my understanding, let's say from like chemistry, like fundamental chemistry, so they are just like charged atoms, right? Charged particles.
Because I'm working on the electrochemical phenomena, okay, so it's not so it's a solid state device, but it's a electrochemical device. So what happens is when you provide the bias, so these ions are mobile, so they can move from one side of the junction. So basically, if they are on anode or cathode, which will they basically are on both the edges. In my case, they can move throughout my sample. Okay, and we can control the motion of it. We can control if we do not even give enough amount of bias. We cannot generate a lot of motion in it. Not only that, if you think it in a way that you can actually reduce the motion of your ion by reducing the temperature. So in my case, if I actually cool down my device to less than 200 K, then you can actually stop process. You can freeze it out.
Okay. So I think to just give to background to the listeners too. What exactly do you do? Like when I said, like photonic devices, like what exactly do you do? Like, do you like fabricate these, or like are these used as semiconductors? Like what exactly is are you doing in the laboratory?
Right. So what I do is called light electrochemical cell, and it's a light emitting devices which works on the primary function of p-n junction. So I use the single material, so to do the doping phenomena. So you can imagine two electrodes, one is anode and one is cathode. You can imagine as a square box, and you put one edge as positive, another edge as negative. You put the silver or aluminum or any metal which is conductive in nature, you provide the bias, and what happens, and then the doping phenomena starts. So when the doping starts from both the edges, one of the edge will have N doping, another one will have the P doping, and they will keep moving because of the ionic motion. You have the charge generation, and then it will keep moving till the point. Then eventually they will meet, and once they meet, it will generate the light. In that process, it is very important to be careful about what is the gap size. If it's too big, the device becomes so resistive that even if you give more and more potential or the voltage to the device, it will not be able to generate some sufficient amount of doping to form the light emission. Right. So
So I was thinking, like the grade school experiment where you have two sides of like two metal, right? And then you plug one into an apple or something, right? Is you have like, so is that type of cell?
yes, it is. It is almost the same thing. The only thing is the property about the material. So the material I have been using is MEHPPV. So it's a polymer, and this has a property to be able to dope both in p doping as well as in n dope.
So could you explain doping? What does that mean in your context?
Yeah, sure. So, um, like you have, because the you can you have okay, let's imagine you have positive charge and you have negative charge, right? So I gave the bias, though the process is very very fast when it's happening, but you can imagine I provide the bias. As soon as I provide the bias, one of your pin is positive, another one is negative, right? So the opposite charge, as in general, will attract towards the edge. So they will run towards the edge. Now all the ions will move, because they are mobile, they will move towards the separate edges. So let's say all the positive will move towards the negative side and all the negative will move towards the positive side. Okay. Now these charges, you can imagine the positive charge. What does that mean? There's a space, right? And then when you have a negative charge, you have an extra electron over there, right? So what that does, it introduce into the MEHPP, which is the polymer film, and when it's introduced into that polymer film, it leads to the generation, or I can say, it provides that electron to my MEH molecule and leads to the doping phenomena, or I should say MEH molecule. PPV is just a form. I can explain that part later. To my polymer, and when it provides that electron, or that provides that that positive or the negative charge to that electron, leads to the generation of electrons and holes. And when electron and holes are generated on the two sides, when they starts moving, and because you have a lot of charges in the solution, and that charge was generated due to some salt present in the solution, then the doping phenomena from the two, we call that as a doping phenomena, which is if you have electrons, surplus amount of electron, and if you have surplus amount of holes, then that's n-doping, and the one extra electrons, then p-doping, right?
We we did our episode 46. We did on transistors and doping and semiconductors and things. So that's also a good one to listen to as a review.
Well, here's the thing, right? Like when I think about doping in solid states, I think more about like adding impurities into your material to have this type of doping phenomena. But what you're saying is like you're not. Are you adding any impurities to the polymer, or this doping phenomena just come from the fact that you're performing this bias?
Yeah, so it we are not introducing any impurity, and not only that, in our doping phenomena, it so because it's not a permanent phenomenon. If we apply the voltage, you have the doping, and once you remove the voltage, it starts retracting. Though the speed will be slow, we have to leave the device for a couple of hours to retract it completely. But you can actually retract it completely. So it's not a permanent doping condition. On the other hand, when you are introducing the impurity, that's a permanent condition.
So in this case, you're saying like you can control the amount of doping from the bias, and it seems like you said the ions you can control basically how much bias are you putting in, and so in the sense consequently you can control the amount of doping then. And if that's the case, like where does light come in? Like where does it start emitting light? Is it a similar let's go mechanism to, let's say, an LED where you have the junction and it emits light?
So you can find some similarity to OLED, but it's not really similar. But yeah, you can say in a way that you form the PN junction. Okay, so when the two fronts, p doping front and the doping front, they meet and emit light. That's the only part which you kind of relate to that thing. Okay, so the release of exciton, but I will not go into that terms, but like PN and doping, when they meet, as soon as they meet, because uh, they can form like a like a uh, in a PN junction device. So what do you call a that region where you have when the two doping front meet, depletion region. So when you have a depletion region, that's the with the formation of depletion region, you have the emission of light from the depletion region. Okay, so these junctions, because as I say, my p and n doping fronts are mobile, so does my junction. So I can move my junction to the left as well as to the right when the doping is moving. And at that time, if because in my case, the p doping is actually more stronger than the n doping, and if it keeps moving and the device is not, is heavily p doped, you can actually end up taking p doping and surpassing the electrode, and it will crush all the light. So you ideally want to have, you don't want it to keep moving all the time, right? You want to keep it at the center as possible. So you have to make some modification in your device so that your junction do not get overwhelmed on one of the direction. Otherwise, it will be quenched and you will not see the light.
So the way I understand, like let's say light emission usually come from the difference in, let's say, an two energy levels, right? There are two states that the system can go. So it jumps down from a higher state into a lower state that emits light. And does it work the same way in this case then? So that depletion region is basically the gap at the energy level in the energy level. Then you can, if you can control the depletion region, then you can control the frequency of the light emitted. Then
So yeah, it so because when you talk about the controlling the frequency or the wavelength of what you can emit, that depends on your material. So if I change my material, yes, I can emit different lights. But you have to change the material because your material works under a particular wavelength, right? Because at least for my material, it is working for a certain wavelength, and it won't, it's not really, I cannot, I mean, I can change the material. There are multiple materials which have been reported with like orange light, yellow light, blue light, green light. So yeah, I even have the green ones, orange one, and the blue one in my lab premises. But yeah,
so I think the burning question is, what's the purpose of these devices? Why are you making these devices?
so these devices has a potential in the application, in a way like you can imagine about the one I'm working right now also is has to do with the uh, with the with the fabrics, right? So you can introduce them into fabric for light emission.
Like fabric, like clothes.
Right. So you
Like
can
polymers.
coat our material because it's very robust and it is air stable. You just need to do a bit of tapping, but it's not need to be that intense. The problem what we face right now is, as I say, that as soon as you turn it on, you can start the doping. As soon as you turn it off, you stop seeing the light emission. So it's like you can imagine it like a switch on and off. You turn it on, you see the light. Turn it off, it's gone.
So it's like glowing clothes.
So we are not like that's just one of the example, but you can actually use it in different harsh condition. So the another advantage is because if you talk about OLED or other applications, you really need to control the thickness of your polymer. You need to be very precise with all the details, not in LEC. So I can have like a very very thick, though not sure how would you make it, because it'll be hard to have a lump, not having a good quality of film. But you can have a really really thick uh, you know LEC basically material, and you can provide just the bias from the top or the bottom or next to each other. Either way, it works in all the configurations.
I can see that, like, maybe you can license this technology to like Balenciaga so they can sell like $10,000 shirt and you can make a lot of money out of that or something. But so are there any like application in terms of the science, like in the like for, let's say, auto scientific devices and such? Like, can this be used as, say, like, I don't know, a transistor or
So there
Anything.
is one potential actually which we have been working on. It can work as a photovoltaic device. So the problem we are facing right now, first I would like to mention the challenge we are facing is the room temperature stability. But if you look at actually the voltage through different inclusion or in our device, we are able to get as high as 65, 64 volts of open circuit voltage, which is like if you think about a photovoltaic device, that's just like not even 1 volt. So you can have a open circuit voltage of like that high. But the problem is, as I mentioned, if you bring it back to the room temperature, all of that got decayed. So you want it to be able to hold as much as you can at room temperature, right? So, but yeah, but if you talk about the potential, yes, it has a potential. Definitely, if you can see even at lower temperature, if you can see the the this high amount of uh, like light emission, then that high amount of open circuit voltage, that means it's a very good photovoltaic device if it works in room temperature.
Right. So when you say photovoltaic, it's like what do exactly you mean by that? Is it some kind of cell? Like I'm not really understanding what you mean by photovoltaic.
I think of like solar panels or something. I don't know. Yeah, they can absorb light and create
Voltage?
voltage. Yeah.
We do exactly the same thing. So we, because in the lab you can replicate the solar light, right, using am 1.5. So we do exactly the same thing. So we cool down our device, we throw that solar light onto the top of our device, and then try to record the performance of our device. So we do exactly the same way a solar cell does record. The only thing is at at lower temperature compared to the room temperature.
So can this be used as a form of energy storage or is it just generating the voltage? Can it store it?
So for the energy storage, we are not sure yet, but yeah, we are proposing something like that right now. But we are not sure. We have not done all the tests, but we are working on that. Can it act as a, or maybe something which can store the device? So the device concept, which is used for LEC, actually has a potential to be used as energy storage. Okay, but the material I'm particularly using right now does not seems to be a very good option in that direction. But yes, if you ask, can it work as the as energy storage? Yes, it can. But the the work has to be done. There have not been any work reported till now, but I know there are two labs. I mean, our lab is doing it right now, but there's also one lab in Sweden, which is working on this part.
At the very least, you can use it for like sensors and things like that. Probably, I'm guessing, right? Because well, I think my understanding is that you can use photovoltaics as sensors because they get some input light source and it converts it to a voltage, and depending on the properties of the light that you're looking for, you can look for certain voltages or things like that. But so this would be. I'm just thinking back to the intro topic, and it's like, if I were to write an article on this, I would talk about how, scientists are studying how to turn clothes into batteries just based on that conversation. Or turn fabric into, like, you can see like how, someone might lead to that because you're turning something that's like a fabric. I don't want to say fabric, but like, polymers that could be a fabric into you're interested in maybe turning into like a storage device for.
Well, you can charge your phone, you put it in your pocket, and you walk out in the sun, right? And you're like, "Oh, my phone charging." Almost like photosynthesis, right? You walking outside, you take the sun, you're like, "Oh, my phone is charging. This is amazing."
Hmm. So it's very like, yeah, communicating these things is it's weird because depending who you talk to, they can completely misinterpret what you say. Um,
I would say that it is possible. The only problem is, let's say, because there have been devices like triboelectric devices, not exactly what we do, but in triboelectric devices, what you do is you do the hand motion. You repeat some motions, and you put it on your feet. You walk around. You generate the charge, right? So you're talking about if I can generate enough charge to turn on the device. If I can generate enough charge with the human motion, then bingo. Yeah, we can use it like that. But remember that the device we are making right now, even if I go for a very small device, my it has a potential if we use some material which has a small band gap. But the material I am particularly using has a band gap around 2.7 or so. So you will need definitely that amount of voltage at least that amount of voltage, considering if there is zero loss, to be able to turn it on. So yes, if we can find a way in which we can generate enough charge by certain motion, yes, okay, then it can actually, or maybe if I can continue keep doing the motion and I attach a battery to it, which can store the charge, and that battery is connected to the device, and then it will work. Right then,
All right, because your device needs some bias to even to start working in the first place. You need energy to do that. So okay, I see. So it's more like so because I wonder because I guess from efficiency point of view, you can have like perpetual machine, right? It's like energy come in and use that to power your bias, and then hopefully we have the leftover energy. But that's gonna be momental, like a Gantuan task, because like to be able to have very efficient machine is very difficult. There are always a lot of loss, right? Like it's not very efficient.
yeah. So I'm thinking in that way. So let's say if I mean I'm not think through that process, but let's say because I say I can use my device as a photovoltaic device, right? So what I can do, because I've seen that if I left my device at lower temperature for like long enough, right? So I can reproduce my result multiple times. So you just need to charge one. I mean, you just need to provide bias one time, and once the junction formed, and if it can sustain that level, right, and keep using it till you can use it,
Oh, you can basically, plug it in the morning and works for a while, something like that.
something like that, for few hours, it will keep working.
Right, because you need to generate a bias, and the bias stays for a little bit, right? It's like it's transient, but it's decaying at a not too fast of a rate. Where so it's not just like like let's say if I take the bias current off, and then it would not just decay within let's say 5 seconds. It would just stay longer. Okay, that's good then. So I think the next question I want to ask is a more like, well, what's like working in this type of lab? Like, can you walk me through like what you do in terms of like because both of us we are theorists, right? We just go look at our computers or our the pen and paper. It's like what's going on there? Do you are you involved in let's say are you working at NFK like fabrication in Kingston where you make your own devices? Like, and what do? You have to do in a clean room? Like, what I don't know what your process is like. Can you walk me through it?
Yeah, sure. So you mentioned NFK because it's a nano fabrication microfabrication center. So we introduced some pattern to our device. Then in my recent research, I'm introducing more pattern to my device, which are 10 micrometer in scale, and it cannot be done through machining process, or at least is not available. That machines which can make a mask of go up to 5 micron or 10 micron is not available in my premises. So I have to go through the microfabrication process. And now if we talk about what I do in the clean room, so when you make a device, because your best performance of your device comes out under a controlled atmosphere. So you need to first understand what is the best performance of your device. And because if you do everything in the open atmosphere instead of a controlled atmosphere, you don't really know what is the efficiency of your device or what is the possible efficiency of your device. And if I directly jump into open atmosphere, yes, my device can survive for some time in open atmosphere, right? And I can make everything in the open atmosphere, it will work, but that's not the best. So to get a correct understanding of the device, you really need to have a controlled atmosphere. So when we have a clean room, you have a least amount of of dust or other particulate matter. And as well as when I'm doing my work, I'm not even only doing in the clean room. So clean room, I'm using it just for for the deposition method. So because I have a electrode, I'm using aluminum or I'm using gold. So I want the deposition method to be happen at a nanometer scale. So if I want to have a very thin layer, you can imagine if I have a gold layer and I can't have a millimeter scale layer, otherwise it becomes too expensive. So you just can have a nanometer scale layers. So for that you need a specialized instrument. So we have a specialized instrument over there, which can help us to clean the device first and then form the pattern. and eventually deposit the material. The second thing I use is the fume hood. So I take my device to the not the fume hood, sorry, I mean the glove box. What you do is you do everything, because you do everything from your hand with your hand. There's no automatic thing in there, but you insert your hand in the controlled atmosphere. So the oxygen and water level is very low, because if you're because we know that all our material and many material which is available commercially, they're always capped, just to avoid the degradation of a polymer under humidity and the oxygen or the real life atmospheric challenge to that polymer. So because if you leave it open, the degradation process become faster. So once you try it, you do all your process, you want to do that at a lower humidity level at a controlled atmosphere condition. So we take it to a fume hood, we do our deposition or we do our coating in that atmosphere. We dry up because we do a heating cooling cycle in our or quenching in our lab to prepare the device. That all happened in the controlled atmosphere. After that, we transfer our sample to the chamber where we do our testing. So for that process of time, we leave it in the open atmosphere. That's completely okay. I can test my device in the open atmosphere. I can see the performance. But during the fabrication process, you want to keep it controlled. And that's exactly the same thing most of the industries follow. So they keep atmosphere controlled during the preparation. And once they do the capping of their device, which is just putting, you can imagine just putting a piece of plastic on the top of it, just to avoid the damage to your device and keep the system intact and the longevity and or the lifetime of your device to be high. You cap it and then you can test it anywhere. Then you can leave it, bring it back to the atmosphere. But during that process, we have to stay in the lab to keep the peak performance as long as possible.
Okay, I was gonna ask, would there be any benefit, or could you even do it? Could you even fabricate this in like a vacuum chamber? Probably not, I guess. And if you don't really need to, it seems like everything seems to be fine as long as you work in a controlled environment. But you asked like the theorists over here, like, oh, if you want a controlled environment, what do you do? And it's like, oh, you just put it in a vacuum chamber. But I feel like that kind of introduces, I don't want to call them mechanical problems, but how do you, if it's in a vacuum chamber, how do you touch it and interact with it and create it? So
Actually, amazing idea. The problem with the vacuum system is it's a very expensive process,
mhm.
right? And the device I'm making is not a very complicated, it's not sustainable process. Yes, definitely. And everything in, if you put the vacuum system, I can't move my hand in and out.
Yeah, exactly, right? And yeah, it's overcomplicating it when it works just fine with a controlled, like a fume hood, right? So,
So we do have our evaporation process because that happens in the nanometer scale. So we need to create a vacuum in those evaporation chamber. So if you go as small as you go, you go to a layer by layer formation of any material in our device, or you go a sub nanometer scale, you have to go to the vacuum system. So what people do in that case is they use a transfer rod. So there will be a chamber which will be in the controlled atmosphere, probably at room temperature or could be any temperature, which is not close to high vacuum system. But then they will transfer it to a small line and then they move to the vacuum chamber so that they can control the cost too. Because having an entire facility, you can imagine, an Intel plant entirely in vacuum, that's a very very expensive thing to
yes,
do.
yeah.
So it seems like what you do all like you fabricate it, you test it, and that's basically the nature of your work. And you do probably have to do a little bit of theory too, right? To figure out like, well, what are you expecting to find and such. Um, oh, I think that's great. I want to move on to, let's say, your background a bit. What got you interested in these? Like these are very specific things, there's like nanofabrication or like these photonic devices. So what's why what got you interested in these? And was it from your undergrad? Because you have an engineering degree, did you?
Right. So my undergrad was in polymer science and chemical engineering. So though my degree was in polymer science and chemical engineering, so I had both the options. I learned both type of courses, but I was more inclined towards the polymer science. So when I'm doing the polymer science, is basically fabricating the polymer, and it's more about synthesis. But I was not. I did that kind of lab work, and I did all the testing of mechanical testing and other testing related to polymers. But I was not very impressed just by using the polymers. I was more inclined towards the device because I want to see those polymers being used in something to be able to for application purposes. So that's why I did my master's in material science. Right now I'm in the physics department, but basically what I do is a semiconductor physics on the fabrication side. So my undergrad was the time when I start realizing, no, I'm more inclined toward the application. I want to make something, though not successful yet, but I want to fabricate something which can actually be used by the people. So I still want to fabric because the lab is more about you do hit and trial, and you don't know which technology you can actually bring it to the level which can eventually be used by the people. But yeah, that's what I like, and I that's what drives me during the third year of my undergrad.
Oh, okay. So I find that, like for, let's say for a practical use, it seems to me that there's always this period of time, sometimes quite long, where you start that when, let's say, a technology transition from R&D into production, right? And sometimes like, okay, oh, this new technology came out, like, and it's being sold, like, but that thing has been around for like, let's say 20 years. So I mean, sometimes it takes a long time for manufacturer to figure out how to scale it up. Because sometimes these devices, you can make it with like, it takes you like a few hours, let's say. But if you have to make a million of those, it's like just take a lot of time to figure out how to make a factory, how to manufacture the devices. Like, are you involved in those type of process at all?
So I have not done the mass production myself. I've not worked in mass production plant, but I work on a company project. During my master also, my project was completely funded, and I was making a solar cell during that time. So it was all a company project, and they have a direction they want to work on. They want to improve the efficiency and what parameters they want to improve. So why it takes a long time, there is one more thing I would like to mention, because not all the technology we do it in the lab, because many things are possible in lab premises and does not make much sense in the large scale premises. And we only do the technical part, but there are other part which a company consider while bringing it to the industry. So even if we are able to make it, let's say, a significant growth in 2 to 3 years, now we find something, they may not like it when they run it in the pilot plant. So it might take another 3 or 4 years to figure out what material or what thing can actually be used and they can eventually use. So, but yeah, I would love to work in the mass production plant. I plan that I will at least work for once in the industry where I can see how the technology which I wanted to be used in the large scale, how does that really work? Someone says as technology at a large scale.
The transition between like academia and kind of industry and real world production is wild. So my partner, she's like a chemical engineer, and she works on like medical stuff, and they want to, they're in a lab and they develop it, and there's like this whole, it takes forever depending on what you're working on, and you need like certain approvals from the government for a lot of things, and there's a lot of like money considerations. And I went to this like conference they had where different people were like pitching ideas to get this specific grant from this foundation of sorts. I've got the details a little fuzzy, but like all like the way you have to pitch it, and then there's so many things to consider that, and like as scientists you don't think about as much, I guess, until the time comes, right? So I think, yeah, we get a few guests every now and then that are interested in this kind of stuff, and me and Feely and Pat, or maybe Patrick is, but me and Feely are just kind of like in our own world over here, and maybe Patrick's a bit more grounded. So I think this is something we should definitely talk about in the future. I should find a guest who knows a lot about this or something.
Actually, I find it very, though if I look at my work, it is very important to use the help from the theoretical sources. Because when we spend so much time in the fabrication, the time to, to simulate things or to understand from a theoretical perspective or a possibility and what actual phenomena is happening is not really that possible. Though I mean, what I'm seeing is I can say, okay, I'm seeing the reality, you are not. But though if you have my thing, what I observe, what I gave you, you can actually describe in a much better way. So most of the simulation people, or I work with one theoretical group in one of other project, they actually come up with a very good reasoning, which sometimes I am not able to do. I'm just able to come up with the right equations to be able to calculate the parameters I want to calculate. They come up with the theory. So it is important. Sometimes they will tell you, okay, maybe you can try making this change if practically possible. So yeah, our collaboration is always needed. Actually, so what you guys do is actually very useful to us, but it's just sometimes we find it hard to relate directly because our thinking process is slightly different. We think about how can I make it work and how can I make it more efficient, and you think about what model can fit in with that. So those two things sometimes doesn't go very well, but it is actually very useful, so we get help most of the time if we can.
Yeah, I imagine there's levels, right? You get like the really theory oriented people like me, and the next level is like the experimental academics. Then you go down to like the engineers, then you go to like the the fabrication and production and business aspect of it. There's all these tiers, and I think the more further between them you get, the more kind of like the bigger the difference. The difference between theory and like the fabrication is huge, whereas maybe the difference between the theory and like the experimental original like creation of the cells or something is there, maybe they're a bit closer together. So bridging the gap is always hard, but there's people do it all the time, and you're right, like it's a big collaboration. Everybody has some input depending on who you have in your project. So yeah, cool.
Well, I want to pivot into maybe a little slice of life question that I want to ask because you have a small child, right? And I wonder, what's that like? What's your grad school experience like having a kid? A lot of us, like actually all the co-hosts here, we all young and we don't have dependents. Let's say, right? But like we had Nathan on a few episodes ago, and he got a few kids, right? But he's incredibly busy juggling personal life and work life and school life. So you got one, but one I think is enough to fill your time. So what has been your experience in grad school?
So yeah, I agree. Like some because so if you study, try to read something and try to think for let's say I want to sit for 2 or 3 hours. I want to have a single sitting of 2 3 hours. That seems like practically impossible anymore. So only and only when he goes to the daycare. So now he goes to the daycare, and that's when I can actually come to the lab and do my things. But I, I love that feeling too, right? I love the feeling of being a father. I like to do the work. Sometimes I don't want to go home. I want to stay in the lab. But probably that's just me. But there are people I know who are more inclined to go back to the home. So sometimes I'm more inclined. So that's the only thing, because you feel like, oh, I did this experiment, maybe it didn't work. I should change this thing. I want to do this thing. So that drives me sometimes. So it becomes, on that part, it becomes sometimes hard. But it was overall, I think the grad school is pretty good. I mean, I have experience in other places. I would say the Canadian grad school is much more relaxed and much more nicer. I can't imagine this situation with myself when I was in actually Taiwan. So I did my masters over there. I was working there, so it was sometimes get more intense. No, so yeah, but it is always fun. So I like it, and I like this feeling too. So I want to have the child. So I have one. So I'm happy.
Well, the thing is, like for me, I stay late all the time, right? Like, and a lot of people who have like dependents or children, they treat grad school can be like a 9 to 5 job, basically, right? You come in, you go because you in a sense, you are limited in time. You gotta drop your kid to school, and then you have to pick them up. You have to. Even my supervisor have children. He has to do that too, right? So, but I think in academia we have a little bit of flexibility on the time too. I don't know about like I know some people have like constraints in terms of lab time, but as a theorist, it's kind of that doesn't really exist except for like some simulation stuff. So I think at least like we have a little bit of flexibility too.
Right, right. So in terms of laboratory thing, so the only thing is when I have to be in the lab, that mostly have to be in the daytime, because if I need some help or if there is an accident, so I have somebody's help. So I have for my experimental work, but generally my experiment do not go over 3 hours for one single experiment. So that's the only time when I have to be in the lab. But when I'm doing the analysis part, or when I'm plotting the graphs and all that thing, I can just do it at home, and that's completely fine. And my supervisor is Jungao, Professor Jungao is actually pretty nice and supportive of that. So I don't need to be there like even 9 to 5. So if I have a plan, and if I, let's say some days I even don't have any experimental work to do. I just have mostly the analysis work to do and the reading work to do. So if my child is feel not feeling well and I have to stay home, then I can stay home actually. So that is
Yeah.
good. I mean, that's good part of academia, that you can take a break if you feels like doing it. Anyways, if you go to the lab and you are not in the right mindset, the chances of experiment to work reduces significantly.
Yeah, it's like you have so many things you have to get done by the end of the week, but you can kind of do them as you have time for them. You don't have to be somewhere at a specific time every day to do them. And I find my group is very much like that. Like it's more like a 9 to 5 to everyone. We kind of we work at our own. We work when we want, when and where we want to. Although again, it's a PhD, right? It's like you have to get stuff done, regardless. So I really like that part of, like, even now it's Friday and it's like 11 a.m. where we are. Like, I should be at work right now technically, but because today I woke up, I'm like, oh, I'm gonna work from home today instead, and I'll get work done later in the day, so it's fine. And even last night, actually, a guy in my group, Josh, he was actually a guest before. He had a kid recently, so the kid, I think it's almost a year old now. Um, but I asked him yesterday, I'm like, "Hey, can we do like a Zoom meeting?" And he's like, "Oh, I'm free at midnight." And I'm like, "Well, I'll be awake at midnight." Like, yeah. So we had like a nice little like meeting last night to talk about something. My sleep schedule's off the rails now, so like I'm up till 2 or 3 a.m., which normally I'm not, but I've just kind of accidentally slept my way into that pattern. So like, I had a midnight meeting with him, and it's that normally when you I would look at my friends and be like, "Oh, you're overworking. Like you shouldn't be doing that." But it's like I didn't really work too much yesterday, so it wasn't a big deal.
Yeah, I mean, I work
Yeah.
the same way. Like by end of the week, if I have what I want to get in terms of my results, and yeah, but it's okay. I'll be flexible with my work, and sometimes it goes. Some days it might go like you, maybe 2 or 3 p.m. At 3 a.m., and maybe other day I can just sleep at 11. So yeah, not bad.
Yeah. I mean, I've been sleeping really late too, and the thing is, we accidentally did that, right? It's there's nothing we could have controlled. But just to pivot to the last question now, is we always ask our guests a slow loaded question here. So I know a little bit of this because we talk quite a bit. And so, what are your hopes and dreams? So I'm talking about who you see yourself being. I know you want to go to industry and such. Do you want to be, let's say, like an engineer, or who do you see yourself being? You still want to work in this fabrication, or you want to more work on the business side? Like, who do you see yourself being in the future? What are your hopes and dreams?
Yeah. So as I say, my aim is very clear. So I don't want to change my field. I want to stay with the semiconductor fabrication. I'm flexible and open to move different fields around semiconductors. So I can move to transistors, IC designs, and all that. But still stick to the semiconductor solid state physics. And then if I can find something, then I would like to start my uh, could be called a startup, or it could be something like that in the long term. But for now, I would like to industry or academia, still R&D. I can see myself as a R&D engineer if you talk, because it's more about fabrication. So I would say, not because I'm not theoretical person. So I would say R&D engineer would be the most ideal position when I'm seeing myself in the next 5 6.
Very nice. Very nice. Well, thank you, Abhishek. I think this has been a wonderful discussion.
Yes, thanks for coming. It was great seeing you again. And similar to our last episode, we forgot to mention at the beginning of this one that Patrick wasn't here again. So again, if you listen to the whole thing, you notice that he has been oddly silent. He couldn't make the last episode, and he couldn't make this episode either, unfortunately, for good reasons. I'm not going to throw him under the bus, but um, yeah, I just wanted to point that out because we forgot to mention it.
Yeah, he's gonna come tell us the story and how to reach us. So stay tuned for that.
Okay, if you would like to contact us, we have many different ways, especially if you're interested in being a guest on this show. So the first way that you can contact us is through our email. We are hyperthesispodcast@gmail.com. You can reach out with any questions that you have or comments about the episode, or you can let us know if you are an expert in your field and would like to be a guest on our show. Another way in which you can reach us is through our Instagram. We are at the Hyperthesis. You can follow us, you can like our posts, and you can get updates of when we are posting episodes. So occasionally we do go on breaks and we might post in between there, but keep an eye on that for our different activities. You can also send us a DM with questions or comments, or if you're interested in joining the show. So feel free to check that out, and you can see what previous guests have been on our show as well. If you're listening to us, congratulations, you have found us. We can be found on any podcasting service, but we are based out of Spotify. But feel free to share us, give us a rating if you can on your podcasting service, and leave comments, leave reviews, whatever you need to do. You can also find us on YouTube. We don't quite have this season updated yet, but we're working on it. And you can check out our last 6 seasons all on there with some very nice visualizations by Feely. There's a lot of ways in which you can reach out to us, in which you can contact us. So please reach out. And if you'd like to be a guest on our show, like the guest that we had today, please reach out and let us know what you want to talk about, and we'd be more than happy to welcome you on our show. So today's story focuses on someone that we've mentioned very briefly in the past, especially when talking about fiber optics. And that person is Sir Charles Kuen. Now, Dr. Kuen, or Sir Kuen, was born in Shanghai in 1933 and lived with his parents in the Shanghai French Concession. There, he studied Chinese classics at home with his brother and was tutored at home as well. He also studied English and French, so he was very multilingual. And today's story will be about someone who was pivotal in the foundation of parts of photonics relating to fiber optics. We've mentioned him on the show a couple times before at least, but really it's interesting to go in depth into his life, as he was a brilliant man who was a Nobel laureate and really was pivotal in developing the techniques and the tools for the world that we know today. If you don't already know who it is, because we have mentioned him before, it's Sir Charles Kuen. So Sir Kuen was born on November 4th in 1933 in Shanghai, China. There he lived with his parents and siblings, and he studied Chinese classics at home with his brother, and he had a tutor at that time. He also studied other languages, including English and French, at the Shanghai World School. But they weren't in Shanghai for too long. So Kuen was still growing up in Shanghai, but after the Communist Revolution, his family settled in Hong Kong in 1949. So not too far away, but at that time a very separate place than Shanghai, and at that time a part of Great Britain. Now, during Kao's time in Hong Kong, he studied at the St. Joseph's College there for 5 years and then graduated in 1952 at the age of 19. And he obtained a very high score in the Hong Kong School Certificate exam, which was the matriculation exam at the time for Hong Kong that qualified him for admission into Hong Kong University, or the University of Hong Kong. Now, Kuen, from a young age, was kind of interested in how things worked and wanted to go into electrical engineering, but this program wasn't actually available at the University of Hong Kong. And so in 1953, Kao went to London to continue his studies in secondary school and obtained his A-level in 1955. So he actually moved all the way to the UK, which again, easy at the time, especially if you're a citizen of Hong Kong. And then he was later admitted to the Woolwich Polytechnic, which is now known as the University of Greenwich. There he attained his Bachelor of Electrical Engineering and would later pursue research and receive his PhD in electrical engineering in 1965 from the University of London. It was there for his PhD that he worked under Professor Harold Barlow as an external student working at the Standard Telecommunication Laboratories in Harlow, England, which in this point in time was a research center for standard telephones and cables. So he was already getting into the telecommunication field. Electrical engineering, of course, has a strong background, and there's a lot of relationships that can be developed between photonics and electrical engineering, whereas instead of dealing with electrons for electronics, you deal with photons. So in the 1960s, at the Standard Telecommunications Laboratory, Kao and his coworkers did the pioneering work to create fiber optics as a telecommunication medium. So he was part of a team that was able to demonstrate that there was a high loss of information from existing fiber optics that were caused by impurities in the glass rather than an actual underlying physical problem. So we know that light can transmit through glass quite easily, and when you extend it in strands, it's not any physical limitations, it's just manufacturing limitations. So then Kao, being a part of this team, was able to work with many individuals who I'm sure you may not have heard of, but these included Tony Karbowiak, who was working under Alex Reeves to study optical waveguides for communications. And in this team, Kao's task was to investigate fiber attenuation, in which he collected samples from different fiber manufacturers and investigated their properties of bulk glass and just saw how light traveled through and how it lost its intensity as it traveled through these cables. So, again, a lot of work already with fiber optics, and these cables did exist, just not in the way that we know them 70 years later. Later, after his attenuation work, and Kao was appointed as the head of electro-optics within this Standard Telecommunications Laboratory, and he took over the optical communication program in December of 1964 because his super, Karbowiak, had left to be the chair in communications at the School of Electrical Engineering in New South Wales, Sydney, Australia. So there, Kao's work really started to be honed in, and they really start to invent this kind of idea of telecommunication over fiber optics and refining the idea and looking at the theories and the optics and essentially how the whole thing worked. So it was a mix of physics and material properties and electrical engineering. And really, by 1966, they had done so much work that they were able to present these results in London and were able to publish them. So Kao was able to publish certain results relating to optical physics and light movement through fiber optics with George Hockman in 1966. And this study in particular proposed the use of glass fibers for optical communication. So Kao did quite a lot of work, especially in terms of looking at how light scatters, different material properties of fiber optic cables, to really understand how light moved through these cables, how it decayed, how the signal decayed, and how you can actually remove these different impurities. And then Kao thought, well, light travels quickly, and if we can eliminate enough impurities and have the signal strength still quite high at the end, how long could we feasibly make these? So at this point, the idea of long distance scales, fiber optic communication start to become more and more of a reality under Kao's research. And so he really tried to work on both the research side and the commercialization of this. He traveled to the United States to see if Bell Labs was interested, but they didn't want anything to do with STL because they were direct competitors. Instead, he found support in Japan, and he was able to visit many different glass and polymer factories discussing the material properties and the actual possibility of manufacturing these. Now, at the time, and still to this day, fiber optic losses tend to be recorded in losses of decibels per kilometer. So that's just the loss of the signal per kilometer. At the time, it was about 4 decibels per kilometer. And nowadays, at least as of 2017, it's around 0.14 decibels per kilometer in infrared wavelengths. So Kao worked very diligently with STL and with his team there, and he was able to publish over 100 papers and was granted over 30 patents, including the water-resistant high-strength fibers, and he shares that with M.S. McLeod. Now, later on, after even more work with fiber optics, Kao joined the Chinese University of Hong Kong in 1970 to found the Department of Electronics, which later became the Department of Electrical Engineering. So he was finally able to bring electrical engineering to the University of Hong Kong. There he was also the chair, of course, of the Department of Electronics, and he built up both undergraduate and graduate study programs for this new school that he had created. He also worked in various corporations, including the parent corporation to the STC in the United States, and was based in Virginia, first as chief scientist and later as director of engineering. 1982, he became the first ITT executive scientist and was stationed mainly at the Advanced Technology Center in Connecticut. And there he also served as adjunct professor to Yale University, and then he also spent some time in West Germany. So he moved around a lot, was involved with a lot of companies and corporations, and he actually ended up receiving the highest award, the Nobel Prize in Physics, which, I mean, it's quite the legendary goal to achieve for a physicist. So coming from an electrical engineering standpoint of things, that's even a bigger achievement. So Kao kind of moved around from then on, working with IEEE, which is the Institute for Electrical Engineers, the Institute of Electrical and Electronics Engineers. And then he was actually knighted later on. So this includes in 2010, where he was knighted as a Knight Commander of the Most Excellent Order of the British Empire. So he's recognized in many different societies and has many different honorary degrees. Really quite an incredible person. He traveled around a lot. I'm sure his resume was probably a small book towards the end of his life. And I think this is reflected in the fact that all of his travels internationally led him to believe that he was a citizen of the world instead of any one country, which truly is incredible. And I mean, is something that I think reflects well on him. Aside from electrical engineering, he was very much into pottery, as well as reading Chinese martial fantasy novels. Unfortunately, he started to suffer decline when he was diagnosed with Alzheimer's disease from early 2004. And while he still did addresses, and of course he was knighted afterwards, there was definitely decline, as I'm sure anyone who has family that has suffered with Alzheimer's disease knows. Towards the end of his life, he resided in Mountain View, California, to live near his children and grandchild. And then on October 6, 2009, he was awarded the Nobel Prize. And unfortunately, in 2016, he lost his ability to maintain his balance. At the end stage of his dementia, he was cared for by his wife and really intended not to be kept alive. He was given a do not resuscitate. He passed away at the Bradbury Hospice in Hong Kong on September 23rd, 2018, at the age of 84. Now, whether you're just hearing Charles K. Kao's name for the first time, or if you are familiar with his work, whether through physics or electrical engineering or electronics, you feel the work that he's done today. The fact that you can listen to this from anywhere in the world means that you're using technology that he helped develop, improve. Truly, the world today would not exist without Kao. And so I think it's a testament that not a lot of people know about him, but his impacts are still felt, and truly an amazing man. So, thank you. And thank you to Kao for bringing us the world we have today, whether for better or for worse.
All right, then I'll see you guys later. Take care.
See ya.
Bye, everyone.